Hey kids, welcome back for video number 2 for Pre-Calc 12. In the last lesson we looked at y equals 1 over x as the main rational function we would encounter, and then all the transformations for that. There's a lot more rational functions out there. They're not all going to be turned intoable, for lack of a better word, into a transformed version of y equals 1 over x. So we're going to need some more tricks up our sleeves to be able to deal with them, and a little more information on asymptotes just in general, and another thing called holes. So I'm just going to jump out of this for a second. I'm going to share my screen so you can see what I'm seeing. And it's going to happen right now. Okay, so you can see Desmos here. That's y equals 1 over x. This is the general version of the simplest reciprocal function you can have. You can throw some things in there like a -2 and it moves the whole thing over 2 to the right, or you can add something in and you can make it go 4 up, but it's still the same basic shape. So I'm going to get rid of that because I want to look at a couple more complicated ones. So that's going to go on. I'm going to look at this guy right here. Y equals 2x plus 3 over x minus 2. I don't know what this equation has to do with anything, but it could come up, you know, in your daily life, right? So what we'll notice about this is you still get the basic, the shape, the characteristic shape of the y equals 1 over x, but it's not exactly a transformation of it. First of all, it looks like it's moved up. We look like we have a horizontal asymptote somewhere. Maybe that's y equals 2-ish. And we have a vertical asymptote at what appears to be x equals 2. And if I want to confirm, I can write x equals 2. And that does look like my vertical asymptote. The graph never actually touches it. And if I want, I can write y equals 2, and it looks like there's my horizontal asymptote. Again, the graph doesn't touch it. But how can we look at this equation right here and determine where the vertical and horizontal asymptotes are? You might notice that on the bottom you have x minus 2, and your vertical asymptote is at x equals 2. Is that a coincidence? And the answer is absolutely not. Where did this one come from? The horizontal asymptote? It's a little less obvious. It has nothing to do with this guy down here. Anyway, we're going to find out what's what. One more thing I want to look at is this guy right here. This one right here, if I show you, it looks like this. Again, same basic shape. But how can you tell that a vertical asymptote is at x is equal to 2? And again, you might know that it has something to do with the denominator, and you might even know the answer entirely. If you factor this denominator out, you get x plus 2 and x minus 2. So I could actually even do this, x plus 2 and x minus 2. Delete the rest of that stuff there, and I'm getting the same graph. Okay, cool. So when x is equal to 2, we get a vertical asymptote. What about this guy? So the astute among you might notice that x plus 2 and x plus 2 cancel out, and that's actually a really important fact. You do not get a vertical asymptote when things start canceling. If I go and click on the value here, x equals -2, and I go to my graph, I actually notice there's a problem. -2 is undefined. Everywhere else on my graph exists, but for some reason that one point just doesn't exist. If you think back to Pre-Calc 11, you remember non-permissible values? Well, 2 and -2 are both non-permissible values. Let's see if I can just get that. I might have to zoom in. But one of the non-permissible values makes a vertical asymptote, and one makes what appears to be a little hole in my graph. So we're going to look at that in more detail, what's causing that and how you can figure that all out. But it has a lot to do with canceling. Anyway, let's get rolling with the notes here. Okay. So what we're looking at today is section 3.2. It is asymptotes and holes. It is a more detailed view. Let me just make sure my pen's working. So what we're going to start by saying is non-permissible values, if you remember from grade 11, or I'm hoping you all learned that, values of x that make the denominator equal to 0. Those are non-permissible values. In a formal way of speaking, if a rational function is defined as f of x equals g of x over h of x, any value a, or x it could be, but just people rate a, if h of a, so something you put in there for x, if that makes it equal to 0, then a is a non-permissible value of f of x. It's basically saying any number you put in there for x, if it makes the denominator 0, then it's a non-permissible value. Instead of non-permissible value, I'm going to write NPV just so people know. Okay, so at non-permissible values, one of two things are going to happen. If there's no common factors between g and h, numerator and denominator, you're going to get a vertical asymptote formed. So in this case, we have x minus 1 over x plus 1, x minus 2. There's no common factors between the top, g of x, and the bottom, which is h of x. With no common factors, nothing cancels out, nothing simplifies, and we can see that when x is equal to -1 or x is equal to +2, you have a problem. You're dividing by 0. What happens when you divide by 0 is you get these vertical asymptotes. If you're still a little unclear on why the graph shoots up when it gets close to vertical asymptote, just remember that if x is not exactly equal to -1 or 2, but really close, like let's say it was -0.9999999, whatever. If we put that in right here, what would the value of this guy be? It wouldn't be equal to 0, but it would be equal to something really close to 0. And if you divide by something really close to 0, you're going to get something really close to infinity. So when x is just to the right of this, that's -0.99999, you're essentially dividing by the smallest number possible, and the graph is going to get humongous. Now, it could get humongous in the positive direction, could get humongous in the negative direction, and that all has to do with the signs. The numerator will be a certain sign, the denominator will be a different sign. We'll talk about that more later, but just keep in mind that dividing by things very close to 0 gives you things that are very close to infinity. Okay. Now, if g and h of x have some common factor, then you get a whole. So when you have a common factor, like let's say x minus 1 and x minus 1, and they can cancel out, you actually wind up getting, you don't have that same vertical asymptote, you just get a whole. The reason why you get no vertical asymptote is because putting in a value very close to 1 on the bottom, well, the same value is going to be on the top. And regardless of how close you get to 0, top and bottom, as long as they're not equal to 0, they'll cancel out and the effect will not make it shoot off to infinity. So you get a whole, which is formally called a point discontinuity or a removable discontinuity. I'm going to call them holes in this course, but just be aware that those are some more technical words. You're going to get a hole which just looks like literally a circle. That circle means this graph is defined everywhere except for that one little bit. This says 1, undefined. That's because at a hole the graph is not defined. You cannot say x is equal to 1. 0 over 0, they don't cancel out. So for only that very specific value of 1, you wind up getting a single spot where the graph is disconnected or discontinuous, which is why these words exist. Because x minus 2 does not have a canceling factor, it still has that effect that when values get really close to 2, this term gets really close to 0, and regardless of what these guys are, dividing by something really close to 0 is still going to make your graph shoot up to infinity or down to infinity. Okay, so you're looking for common factors to find holes. Solving for the coordinates of a hole. So the non-permissible value always gives you the x coordinate of a hole, but you can't figure out the y coordinate without doing some math. You have to solve for the y coordinate by substituting the non-permissible value back into the simplified equation. So what this means here is, in our last example, if we knew that x equals 1 is the problem, we would substitute it back into the simplified equation. You'd have to cancel those out, and this would simplify down to this, and you'd substitute it back in, and you'd figure out that the coordinates of the y coordinates of the hole is whatever this is, which I guess is -1. If you tried substituting it back in without canceling, you're going to wind up having a divide by 0 situation. So you cannot substitute it back into the original equation. You have to put it back into the simplified one. So let's look at this example here. Determine the coordinates of the holes. The very first thing you must always do, and say it with me, children, I can hear you all the way from here, factor, factor, factor. So x squared plus x minus 6. Okay, I'm going to have to remember how to factor here. So let's see, x and x. Two numbers multiplied to negative 6 and add up to positive. That's got to be what? X plus 3 and x minus 2. When you factor the top and the bottom, you can see that before you cancel, you should point out the non-permissible values. So the non-permissible values are when x is equal to 2 or negative 3. Now you cancel those bad boys out because this simplifies down to this. As long as x is not equal to 2 or negative 3, this is a correct simplification. So what we do is we would say, because we had a canceling effect, this tells us we have a hole, not a hole, we have a hole at x is equal to 2. What are we going to have at x is equal to negative 3? The vertical asymptote. But we're interested in finding the holes. So what we do is we're going to find the y coordinate of the hole at x is equal to 2, and we're going to take this equation here, we're going to go y equals x plus 2 over x plus 3. We're going to substitute in the actual value for x so that we can figure out where this is, and we can see that y would be equal to 4 over 5. So we can therefore conclude a hole is located at 2 for x, comma 4 over 5. And because it's always worth looking at this stuff, let's have a quick look. So x squared minus 4, let me just check here, y equals x squared minus 4, and the bottom was x squared plus x minus 6. So when you look at this, we should find that we have a vertical asymptote at negative 3. So let's actually just type that in. X equals negative 3. There's my vertical asymptote. And the point where we have our hole should be right here when x is equal to 2. And we can see that on the graph 2 is undefined. Now, if you're going, well, okay, how can I test that my value is 2 comma 4 over 5? We can actually type this in, 2 comma 4 over 5. And you can see what Desmos did for me was it actually plotted a point right there. So 2 comma 0.8. So that is where my hole is actually located. And if I make that disappear, now I can see that is where the hole is. So Desmos will never tell you the y coordinates of the holes. You have to figure it out. Okay, moving on. For the following function, state the domain and write the equations of vertical asymptotes or holes. So this is definitely one of those situations where you should actually take a second, think about this, try it now. Okay, so what we're doing is we're always going to factor. Now, the top is not factorable. The bottom, you sort of can factor it. This is sort of iffy. You could factor like this. It's a little weird to factor not over the integers, but it's definitely worth doing. So does this have any holes? Nothing cancels. Does it have any vertical asymptotes? Absolutely. We look at the non-permissible values, and they're located at x is equal to plus or minus root 3. So we're going to have 2 vertical asymptotes. Vertical asymptote at x equals plus or minus root 3, and no holes. The numerator, by the way, has nothing to do with vertical asymptotes. Okay, so it's pretty simple. We've written down our vertical asymptotes, and we've determined that there's no holes, so we don't need to determine the coordinates of any holes. Okay, example number B. Yes, I know that's not a number. So factor first. This becomes x minus 3 and x minus 1. And then on the bottom, it goes x minus 3 and x minus 2. So we can see right away, we're going to have to look very carefully at x is equal to 2 and 3. We can see what happens. We have some canceling effect. So we can conclude there's a hole at x is equal to 3, and there's a vertical asymptote at x is equal to 2. So to find the hole's y-coordinate, we're going to take the simplified equation. So this whole thing simplified down to y equals x minus 1 over x minus 2. And then we're going to enter the value x equals 3. So 3 minus 1 over 3 minus 2. And this becomes 2 over 1. So the y-coordinate would have to be 2. So what I can therefore conclude is the hole is at 3, 2. Vertical asymptote, that's the equation. Hole, do not just stop saying x is equal to 3, you have to give me the coordinates of the hole. Okay, last one. Why did I do this to myself? First of all, what are the non-permissible values at the bottom here? Does this mean we have to use something from last chapter? I almost said last year, it feels like so long ago. Yeah, you're going to actually have to factor the odd denominator because we can't find the non-permissible values without doing that. So you have to remember the whole thing here. So if you remember, we have to take a guess at a value of x that makes this equal to 0. So I'm actually going to take this, I'm going to call this my polynomial. P of 1, I'm going to hope I get lucky. I'm guessing I made this easy on myself. I haven't done this example in a long time, but let's go and hope. Let's see, 1 minus 1, negative 2 plus 2. Phew, the whole thing is equal to 0. So this tells me x minus 1 is a factor. Okay, I'm also going to synthetic divide here. So if you remember synthetic division, 1, negative 2, negative 1, and 2. 1 times 1 is 1, add those up. Negative 1, add those up. We have 2, we get a 0, and we get x squared minus x minus 2. I think that's actually factorable as well. So this becomes x minus 2 and x plus 1. Okay, so when I actually factor this whole thing, and you have to factor it out entirely because this tells you all of the non-permissible values. So we have NPVs at x equals, let's do this in order if we can, negative 1, 1, and 2. The things I cancel here are these guys. So this tells me I have a hole at x equals 1. And I have vertical asymptotes where things don't cancel. So at x is equal to negative 1, 2. The coordinates of the holes, y equals, we're going to write the simplified version so that x minus 1 factor is gone. And we're going to substitute in this guy into that. Sub in x is equal to 1. Okay, so y is equal to 1 over 1 minus 2, 1 plus 1, and that gives me 1 over, well, okay, I know this shouldn't be hard, but for some reason my brain's just working slow. So what's that, negative a half? I hope I did that correct. That's my y-coordinate for my hole. So I can therefore say, just give myself a bit more room, therefore say my hole is at, a little at symbol there, 1, negative 1/2. And I can also just summarize here the vertical asymptotes, x equals negative 1, 2. Okay, I just did all that work. Now I actually would like to check it. So I'm going to see if I can remember all this and type it into Desmos. So we're going to go x minus 1 on top. And what we had here is we had x cubed. It was minus 2x squared minus x plus 2. So minus 2x squared minus x minus 2 plus 2. Nice. Okay, Desmos, stop it. That is correct. Okay, so when I zoom out, I said I had asymptotes at negative 1, 2. So x equals negative 1, there it is. X equals 2, there it is. And I said my hole should be located at 1, comma, negative 1 over 2. So there's one spot here on my graph that's marked, and that would be where I'd have my hole. You don't actually see the holes on Desmos, but if I go to click on it, one is undefined. So there's my hole. I can find it, but I have to actually go and click on it. Great, so done. Horizontal asymptotes. I actually think what would be really fantastic is for me to break this up into a second part here. So I'm actually going to stop the recording right now, and I'll start this up and call it part 2. Thanks for watching.